Okay, good afternoon, ladies and gentlemen. Today I have the pleasure to introduce Václav Mácha from Institute of Mathematics, Czech Academy of Science. And since we know him very well, but anyway, I will introduce you. So Václav, he did his PhD with Professor Jana Stara. Then he continued as a postdoc in our institute, it means Institute of Mathematics. Then he was like 1.5 years, something like this, in Yonsei University in South Korea. Then he came back and joined our team, and nowadays he's independent researcher. And today he will speak about analysis of a system modeling the interaction between the motion of piston spring and viscous flow. So,
okay, so thank you for introduction. Actually, I would like to talk about this work, which was written jointly with Sabrina Shebly and Nečas, who introduced me, of course. And actually, Sabrina Shebly, she was a postdoc at our institute. I don't know about the student postdoc. Okay, so eventually we did in common this fluid structure interaction system. Yes, so this is a system which consists of a piston spring and of the compressible flow. And actually, the problem comes from some application. Actually, there is some idea behind, because there is a group of people, say from numerics, from the Czech Technical University, who are interested in biomechanics, and especially one of the problems they are treating is the behavior of human lungs, or say the bronchial tubes, in the proximity of explosion. Yes. So one can imagine that there is a man somewhere nearby, they're exposed some kind of bomb, and they are trying to model somehow how the lungs are behaving then. Yes, and therefore they came with this problem, and they say, okay, so let there be a tube, which is say this bronchial tube, and on one end there is an inflow, which is actually this like bomb-driven inflow. Yes? So there is some kind of pressure wave or shock wave or whatever, which due to which there is some huge intake of air. And on the other hand, there are lungs. Yes? And there is this question: what happens if we suddenly forget about this inflow? Yes. So let there be an inflow prescribed, and then we would like to have something like nothing condition. Yes? So once the explosion is over. So in order to model the human lungs, we decided to put here some kind of piston, which is actually ended by a spring. And okay, so one can include here also some kind of damper. And there is, of course, this question how the system behaves. And as I said, till some given time, say T star, we will expect that there is an inflow prescribed. And then it would be great to have do-nothing boundary conditions. Yes. So just to see how this whole system reacts after the certain times T star. It turns out that this do-nothing boundary condition is actually nothing, say, trivial in the case of compressible flow. Yes. So once we don't know anything about the outside environment or whatever, it's very hard to prescribe any kind of outflow, sort of do-nothing boundary condition. It's not just a version of incompressible flow. So, like, we simplify that one and we prescribe actually like given outflow. Yes. After a certain time. And we are interested in this one setting. And as you can see here, actually, like if this is our domain, then on one end of the domain is assumed to be open, and on the other hand, on the other end of the domain, there is assumed to be, say, piston whose mass is eventually 1. Yes. So we end up with this system. So let me just describe it. So the first two equations, they are say, just the compressible version of the Navier-Stokes equation. So here we have the mass conservation law. The second one is the momentum equation. And then, as you can see, up to this time t star, we assume that there is a given inflow. So there is the velocity and the density prescribed. And starting from some time t star till the time capital T, we are given the outflow, which is this time given just by the velocity. And of course, like the density on the outflow is, say, part of the unknown. Yes. So on outflow, we have actually this density rho. And then there is this equation for the movement of the piston. Yes, so for this one. So the position of this piston is prescribed by this unknown b, which is actually time-dependent function. And here you can see the whole equation. Actually, here on the left, this is the usual evolution equation for the evolution of the position. Yes. So actually, the second derivative of b plus the stiffness of the spring times the displacement of the spring plus, and okay, so this L is some stiffness of the damper times B prime. If there was no fluid, that would be equal to 0, but actually there is an action of the fluid on the piston, and this action is described by the stress tensor, which in this one-dimensional setting is just the pressure minus mu times the derivative of mu. Yes, so this is the evolution of the piston in this.
When the first equation it should be wrong.
Oh yes, of course, yes. So this is yeah, for sure.
No, this also partial derivative. So we use index t for partial derivative and
yes, yes, yes. It's for me. It's the same. I know. Like I'm sorry for those of you who are like. I know that some of you make some differences, but for me, like always, like. Okay, so I'm using this dot is used especially for functions which are just t dependent. Yes, this b is just t dependent. Yes, but yes, so yeah, so that's it.
So this is
Yeah.
Okay. Yes, then of course the velocity of the fluid at this end, like the piston, is equal to b prime. Sorry, b dot, of course, and we are given this boundary, this initial condition. Yes, so this is the system we would like to treat, and yes, so actually I'm going to show you how to what we did. We just provide the existence of strong solution to this kind of system, and yeah, so let me go. So first of all, we rewrite it into Lagrangian coordinates. Yeah, so we introduce this kind of Lagrangian mass coordinates. So y is equal to chi of tx, where actually chi of tx is equal to the integral from dt till x of rho ts ds. Actually, yes, so maybe I can go here once again back to this picture. So here is actually 0, here is bt. So the x itself is from 0 to bt. So this means that here y belongs to minus eta t equal 0, but actually this eta t is the total mass of the fluid, which is contained there. And if we differentiate this eta t, Okay, so once again, I use another way of how to find time derivative, but I'm sorry. Okay, so it's still like the derivative with respect to t. Then, okay, so if I integrate the upper integral there, so what I obtain is an integral from 0 to dt of dt rho dx plus rho t at the point dt times v dot t. And now to evaluate this integral, actually, I can use this continuity equation. And I obtain here minus integral from 0 to dt of dx rho u dx plus rho t dt times v dot t. And this is equal to, of course, like now this to evaluate this integral, one has to evaluate this function at these 2 points. So there will be rho t dt times u t dt minus sign plus rho t0 u t0 plus rho t dt times v dot t. And eventually this velocity is equal to this v dot. So these two terms cancels, and what remains is exactly this time derivative of theta. Okay, so this whole integral. And actually the total mass, if we are in this intake area, yes, so no area, intake time, say. So for times between 0 and t star, the total mass is given. Yes, so here is the total mass at 0 plus this u in, rho in integrated from 0 to t. Yes, so these are these boundary conditions. However, for the times in between of t star till capital T, yes, and this is actually the outflow, the total mass is unknown because actually this rho is the solution to the equation. Okay, so with this coordinates at hand, I'm going to introduce new variables. So actually, there is this characteristic volume, specific volume, yes. So V is equal to 1 divided by rho. U tilde is equal to U. Okay, so this is once again the velocity field, but now in this Y coordinates. And actually, I replaced the function P, the pressure itself, by Q. Okay, so I forget to mention that we take the pressure to be the usual one. So actually for us, P rho is equal to rho to the power gamma, even though I'm quite sure that this is not necessary, but later on I will use that in some calculations. Okay, so this is the new system which we obtained. Yes, so once again, this is this continuity equation, linear momentum equation. Here we have the equation for the spring and the behavior of U on one hand, on one side, or sorry, on one edge of the domain. And once again, if we are with time in between this 0 and t star, we have this inflow boundary condition. These are quite nice. If the time is over this capital T star, we have this outflow boundary condition where actually this V is an unknown function. Okay. So this is our aim now. And actually here still we have only Y in this interval from minus theta t till 0. And as I said, for the case of inflow, it's quite fine, it's given, but for the case of outflow, this is not very good because this domain is actually an unknown for us. Okay, so I would like to present also the next coordinates, just to rewrite this system into the fixed domain. So we just take, yes, we just take a new unknown z, which is just simply y divided by minus eta t. Yes. So this gives the new coordinates z to be in between of 0 and 1. And of course, then the system is significantly changed. So you can see it here. There actually arises new constant alpha and beta, which are actually eta dependent. So you can see them here. Yes, so it's either -1 divided by eta in case of alpha, or it's actually eta prime divided by eta times minus z in case of beta. And we just simply obtain this system. Once again, for the inflow, this alpha and beta are given. And for the outflow, unfortunately, this alpha and beta are, say, part of the unknown. Yes. So now I would like to present here several theorems concerning its existence. So first of all, I would like to treat the inflow case. And in case of this inflow, I would like to present just the theorem. Time t0 such that there exists a solution rho u and v in this regularity class to the given system. Yes, and also we have this estimate for the time derivative of density and time derivative of velocity, and also this 1 divided by rho is bounded. Yes, so this is something which is, let me tell it once again, known, which is due to Mácha, Takahashi, and Kusnak. And basically, this is the reason why we introduce here this particular system, because they also work with this one. Here, everything is more or less nice because like these coefficients are known. Yes. So this is this local in time existence. And of course, I have to tell a few words about the global in time existence. Actually, this is once again not that difficult. The global in time existence, actually, in the case of the outflow, I will tell you more, and the inflow is then just say a simplification. Yes. So I will not comment on this global in time existence here, but rather than then I will say a few words later on when I will tackle the outflow case. Yes. So let me stop here with this inflow and let me proceed to the outflow. Yes. So first of all, I would like to erase the blackboard because I would like to write here several formulas. So actually, I would like to say a few words about this local in time existence. So once again, we assume some H1 regularity on the initial conditions. Here, I assume that these initial conditions are actually basically in the time capital T star. Yes, so this is the time where we switch from this input to outflow wells. So actually, these one are the initial conditions. I also assume that this U out is in C1. Yes, so this outflow is given by a sigma function. And then I actually claim that there exists strong solution on some time interval T star to T1, where T1 is greater than capital T star. Yes. And the way how to prove that is actually based on this proposition. So we are introducing this this operator capital S, which acts on this set psi. And actually, if we take any, say, eta out, we are able, so let me go back, we are able to compute from this eta out here these constants alpha and beta. And we are able to use once again the approach by Mighty, Takahashi, and Tutsnak in order to deduce the existence of V tilde and underlined U. Yes. So once we are given this eta out, we have these coefficients here, and it's perfectly fine to compute a solution. Yes. And okay, so here I'm using the solution rho and V tilde, but this is actually the same. And based on this solution, I compute this S of eta out, which is actually a new eta out. Yes. So this is a formula which should be satisfied by this eta out. And once I find the fixed point of this eta out, this will be the solution. Yes. So of course, like that's the point here, and this is behind this proposition. So first of all, I would like to take this set of C1 functions, which are given such that their value in the point t star is given, and their derivative is negative and bounded from below by some capital, lowercase m or minus m. Actually, the m is a constant which is greater. Okay, so this is not true. There should be greater than something different. I will soon show you what. And one can show that actually this m for a certain choice of this m and t1, this S of psi is a subset of psi. So this S maps psi into itself, and the mapping is a contraction in a C1 norm. Yes. So there's the point here. Okay, so maybe I will not show here this calculation right now. There will be more of these. So just for a while, try to trust me. So this is fine. And next, like we are able to prove this one. And concerning this global in time existence, we would like to prove some further estimates of this solution of rho and u. Sorry, of v and u. And actually, once again, let me go back. So from now on, I will use basically this system. Yes, so I will work with t until the u, and these are the variables in the Lagrangian coordinates. And for that, we have actually several estimates. So first of all, there is this mass conservation. So this is an integral from 0 to b from rho dx. And okay, so I showed here that this is actually rho t 0 times u out, but u out is negative, so this is less than 0. And therefore, I can deduce that the integral over the rho is less or equal than some initial constant. Yes, so this is the first estimate of the solution. Moreover, by the method of substitution, one can get that the integral of the specific volume from minus eta out to till 0 is always equal to b t star at time t star. And this is actually not only true in this time capital T star, but it's true for every times t. So one gets this additional, say, a prior estimate. Yes, so this is an integral from minus eta out to 0 of a vty dy equals vt. Yes, so we have these two estimates. The next one is, of course, the energy estimate, energy conservation law. I'm not going to, okay, so maybe I can, but like this is kind of like a usual energy estimate. Yes. So of course one just has to take the product of the linear momentum equation with U, and actually what is here kind of difficult to handle is the boundary conditions, but the boundary conditions give rise of this one. Yes. So the energy estimate here is minus capital Q over V is actually the potential of the pressure. Yes, so this is just the usual like kinetic energy plus the potential of the pressure, which is here formulated as you can see. It's actually minus Q over V. Then there is this energy of the spring. Yes, so this is actually V dot T square divided by 2. So this is okay. So this is a kinetic energy of the piston. Yes, of the point mass. And this K half times Vt minus Vb, this is the energy of the spring. Yes, so the potential energy of the spring. And then one has to hear this dissipative term. Yes, so this one. And this term is also, say, positive. Let me just recall that the U out itself is negative, so the whole thing here is positive, so it's fine. This is this energy conservation law. Okay, so next, we are also able to deduce some density estimate. Okay, so I would like to explain this. So actually, we establish a function capital N over V, which is equal to mu times the logarithm of V. And then its time derivative is equal to mu divided by mu times dt. And actually dt is u tilde x. This is by continuity equation. So eventually, I'll go back, likely, somewhere here. Oh, this is something what appears here. So I can write down now the mu tilde t plus uy is equal to m ey. And now I can integrate that one. Okay, so I need my papers for a while because, say, here if we have this domain, so this is actually time t star, this is some time t. This is the domain from 0 till minus eta t. And okay, so the domain is along something in this way. And I would like to take this equation and I would like to integrate from this time, from this point, which is actually t star 0, to this point, which is actually t y. And if I integrate this equation, I should get minus capital M at t y equals minus capital M t 0 plus capital M t star 0 minus capital M t star y plus integral t star q to 0 to minus integral t star t q to y to and this is not the end yet, because then there is this minus integral from y to 0 of u t star s minus u ds ds. Yes. So that's something actually what we get upon integrating over this region. And actually, I have also formula for this Q to 0. This formula is actually here. So here the right-hand side is evaluated exactly at the point T0. And therefore, I can write down that Q0 equals the time derivative of T plus the second derivative of T plus L times the first derivative of T plus K times T minus T. Okay. And of course, now I can take this one, plug it here, integrate from T star to T. And actually, surprisingly, this disappears. So this is no longer there. This cancels with that one. And eventually, I should get something like minus n T y equals minus n T star y plus. And okay, so there will be T dot at T star, sorry, at T minus T dot at T star plus L times D at T minus L times D at T star plus K times integral from T star T T to minus D. Okay, so this is actually this term minus an integral from T star to T over Q. So y into minus integral from 0 from y to 0, and there will be u T star s minus u T s dash. Okay. And now I'm representing this boundary. So that was actually my aim, because I've got the energy inequality. So here, like whenever there is this B dot or B is perfect, it's bounded to the energy inequality. And the only thing which is actually not that much bounded is this Q. Yes, so this integral from P star to P of Q. But the integral itself is positive. So here it is with negative sign, so I can forget about that one. And this can be bounded by the means of kinetic energy. Yes. So eventually, this is less or equal than C, which means that NPY is greater or equal than, say, minus C for some C constant. And because of the definition of the potential itself, we can obtain that, say, 1 divided by B is bounded from above. Yes, okay. Like surprisingly, I can use this information because 1 divided by B is bounded from above. I've got bound of that one also. Yes, and I can bound the right hand side from above. Yes. Oh, sorry, from below. And this gives here the second estimates this D belonging to L infinity. Okay, so I will not go too much into details in these further estimates. So let me just tell that, like, it is also possible to use this potential to prove that the density itself is bounded in L infinity H1. So just maybe some idea. I want to keep this one. Maybe I will use here. Second blackboard. So actually, I can rewrite this one as u minus n y time derivative equals minus q y. This minus q y can be expressed in the means of this m of y, and actually this can be as well multiplied by u minus m of y. Yes. To deduce eventually the boundedness of L infinity norm of L infinity L2 norm of this u minus m y. Yes, and this L infinity L2 norm is sufficient to deduce this bound that V belongs to L infinity in H1. Yeah. And the next bound, so this is some further velocity estimate. Once again, I will not go too much into details. So here, I would say this is, say, usual testing by Laplacian. Yes. Even though it's usual, like there are these boundary conditions which brings some non-trivial problems. Yes. So it's not that much usual, but okay. So anyway, I don't want to go too much into details here. Yes. Okay. So, but eventually, I've got this estimate, which is important there. So this U tilde is in H1 for every time t. V is in H1 for every time t. And I've got this bound, yes. And this is something which allows me to extend the solution to another time interval. So we actually deduce that the strong solution exists on a time interval t star from t star to capital T for any given t if we additionally assume that the position of the piston is strictly right from the zero. Yes, so actually the domain has to not link to zero eventually. Yes, and now there is this question, like what is the maximal time of existence? So if we are somehow able to deduce, so what's this capital T? So in particular, I would like to write here one additional estimate. Okay, so actually here, I would like to use this last line on the blackboard. Because of course here is minus or say logarithm of V. I can basically deduce from the last line and from definition, I can deduce that say 1 divided by V T Y is less or equal than 1 divided by V T star Y times, and here I would like to say something e power to G T, where this GT is basically like all this sum. Yes, so it contains all the remaining numbers, and actually this GT is bounded by the energy. Yes, and therefore I would like to get some lower estimate on VT, and we saw that this is equal to integral from minus eta out till 0 for V y dy. And here I can use that one. So I can say that this is greater or equal than e power to minus gt times eta out times the minimum over y of t star y. Definitely. So that's fine. So let me denote this by C and this by C. And actually, I can write this C times eta out. And this is greater or equal. And now there is C times And this eta out at time t can be written as eta out at time t star, so which is actually 3 squared because this is the initial condition plus, and there will be integral from 0 to, sorry, from t star to t of u out times the minimum of v t minus eta out. And here the minimum is taken over or tau in t star. And once again, so this is actually bounded by this one. So I can say that this minimum is once again some kind of a constant, which actually depends on the initial specific volume and some energy. And therefore, whenever this is positive, then the solution exists. And I can claim that the solution exists till the time where we take it out from t star to t of u out t dt equals minus eta out of t star. Yes. And here this capital C actually depends on the initial condition. Yes. So even though this this result seems maybe kind of local, we are able to give say the lower bound for the maximum time of existence. Yes. So that's basically okay. So this seems to be the end. But if you give me a while, actually, this is not the end. I've got one additional things I would like to announce because me and my colleague, we are preparing summer school, and I would be very happy if you can take a look in this particular web page. So it's effect.math.sas.cz. It will be this June, since 17th till 21st. And actually, I think that we have quite good speakers here. Here you can see some of them. So Elia Brück, Gianluca Kripa, Yankio Choi, and Ivo Murata. Yes. So I would be very happy to spend some time and take a look there. And if you also can spread this information. Okay. So thank you.